Okay, lecture 26, review, covariant derivative and connection. You see, this is Christoffel symbols is called as a connection. Now, to understand the origin of Christoffel symbols in differential geometry, consider the curvilinear coordinates x1, x2, x3, and the points P, x1, x2, x3, that is a curvilinear coordinate, and Q. Okay? Now, you see this figure here. This is the origin. This is position vector R at P, position vector R of Q. You see, you define the basis vector. You see, this is A1, A2, and A3 at P, and A1, A2, and 3 at Q. Now, you see, then you have the basis, okay, at point P and point Q. Now, let's consider, okay, this definition of AR. AI is partial R respect to xi at P. Attention, is different from the partial derivative of R respect to xi at Q, because we are dealing with the curvilinear coordinates, okay, the flat space, okay, the basis vector doesn't change when you move from one point to another. That's a big difference, okay. There's a curved surface in this case. Now, this over here, let's take the derivative of xy, partial derivative, with this A sub j, okay, partial R respect xj. You see, I can, you see, swap, okay, the derivative here, then partial AI respect to xj is equal partial aj respect to xi. Now, let's develop the covariant derivative with respect to a scalar t. In general, in the literature, you will find is scalar lambda. Okay, I set t over here. You see here, this is acceleration. Okay, when t is a time. You see, there's acceleration. You have to develop. You must develop this d of dt of ei a sub I. That's a vector. Okay, vector v. You see, this is using the product rule. Okay, you can see easily that this is di dt ai plus vi di of dt. Attention, in curved surface, in curvilinear coordinates, this here is different from zero. Okay, now then you can see, now that's a point. Okay, let's remark this term over here on this equation 1. This equation 1, let's emphasize this term over here. Okay, this is related to the curvilinear coordinates. You see, now di of dt. Okay, this is vi. Now this is a chain rule. Okay, because x is a function of the parameter t, or parameter lambda in general. So this xj dt partial xi or dxj. You see, you can see this as you cancel here and reproduce the left hand side. So dxj dt is component of velocity. Okay, if t, the parameter is the time. Okay, in general, we don't talk about velocities because this scalar function could be any, like lambda, for instance. Okay, then I call vi vj, partial xj, partial xr respect to xi. You see, now this over here, you see, you have vi vj, second derivative of the position vector r respect to xj and xi. You see, attention, I and j here are dummy, okay? Dummy indices. See, that's important just for you to see. Now, this I call relation 2. Now, from 1 and 2, you see, this is 1 over here, okay? This is 2. I just substitute. You see, I call capital S the vector. You see, I define as second derivative of r partial, okay, with respect to xi, xj. Now, you see that S, I can't, this figure here, you keep, that's show clearly, okay, that the vector S at point P, I can decompose, okay? This is S2ij A2, this red one here, it is Sij1 A1, okay? And this over here, okay, this, that's called, this coordinates, okay, that is Lijn, okay? That's perpendicular to this red one, okay? Now, why is this here is important? Because we always we work with the covariant contravariant coordinates, okay? And then the covariant coordinate is x1, x2, and x3, okay? Just instead, you see, these are discrete contravariant coordinates, okay? This. I can work the same point using this x sub I, okay? And x sub j, okay? This is this covariant derivative which belongs, attention, to the dual, okay? This here belongs to the vector space. Now, this perpendicular A3 over here, you see, this is I set over here, this is A3. Okay, I put A3, I repeat, okay, sorry, I will change this before, okay, this A3, okay, is just, I reproduced this figure here at point P, I reproduce right here, okay, x1, x2, and x3, you see they are curvilinear coordinates which belong to the vector space, not to the dual. Now, I can represent the vector S, okay, just a projection, okay, on the tangent space and perpendicular to the tangent space. That's what I said. This perpendicular over here, and you see, attention now. I think this is 3 over here. You see, attention now that I will have over here, you see, A3 over here is different from this A3 over here, you see, because these are perpendicular to A2 and A1, you see, because A3 belong to the basis, okay, of the dual basis, okay. Now attention this is a upper 3 here, and this is lower 3 here. You see, this belongs to the curvilinear coordinates at point P, the x sub 1, x sub 2, and x sub 3. Okay, it's different from this one. Okay, this one is the indices 1, 2, and 3 are upper. Okay, and this is a lower. These over here are properties, okay, of the differential geometry, which you can see here in part 1, 2, 3, okay, on these several videos. You see, this is part 7. You see, this is part 7, okay? Just to review, A3 is perpendicular to A1 and A2, okay, by definition, and is the unit vector, orthogonal vector A3 divided by the modulus, okay, of A3. Now, AI dot AJ is Gij by definition, and AI dot AJ is Gij. You see this here, the indices shows that Gij are covariant, and these Gij over here are contravariant, okay, which belongs to the dual space. Now, again, Gij is a property, is Aj. You see, Gij is Ai. That's a property of Gij, with I demonstrated, okay, previously in part 1, 2, 3, you can see there, okay. Now, Gij Ai, now delta Ij Ai is Aj. You see, there's the properties that we derived before, okay, previously. So, the vector S, I can represent this just from this figure over here, okay, I just transpose to here. So it's Sij1, A1 plus Sij2, A2 plus Lijn, okay? Remember, n is the normal vector which is perpendicular to the tangent plane. You see, there is a tangent plane at P, and n points, okay, outward, okay, in this plane, tangent plane. Now, let's take the dot product on both sides.